Hello, this is Dr. Hanaa Assil, and this is a second part of chemical bonding in which we'll be talking about the different structures, whether they're simple molecular structures or giant macromolecular structures. So let us take a look at the difference between these two types of structures, molecular and giant. So what do we mean by simple molecular structure? Simple molecular structure is in which we have the individual molecules separate from each other with only weak forces between them. For example, if we say we have water molecules, each molecule is separate from the others, but there is very weak intermolecular forces. Intermolecular forces means the forces between molecules. So if we have molecules like the molecules of water or molecules of carbon dioxide, these have weak attraction forces between the molecules, and as a result of that, simple molecular structures always have low melting point. Now, if we say, why does anything, any substance, have a low melting point? Why does water, carbon dioxide, oxygen, chlorine, why do they have low melting point? This is because of weak attraction forces between molecules. We have weak attraction forces between molecules. These are called intermolecular forces, and these need a very small amount of energy to be broken. So if we heat it to just a little bit and the molecules separate, that is what we call a low melting point. So remember, most substances have simple molecular structures. And if they have simple molecular structures, then they have low melting point. Why do they have low melting point? Because there is weak attraction forces between molecules or weak intermolecular forces that need a small amount of energy to be broken to separate these molecules so that they can either melt or they can boil. So this question says carbon dioxide has a low melting point. State the general term for the weak forces that cause carbon dioxide to have a low melting point. We said molecules like carbon dioxide have low melting point, and we said why do they have low melting point? We said because they have weak attraction forces between molecules. Now, what is the general term for the weak attraction forces between the molecules? We call them intermolecular forces. Silicon tetrachloride has a low melting point because it has weak forces of attraction between particles. Now, name the type of particles that are held together by the weak attraction forces. So if I tell you that the silicon tetrachloride has weak attraction forces between what? Between molecules. So these are the type of particles that are held together by these weak forces of attraction. Giant macromolecular structures are large three-dimensional structure in which there are many atoms strongly bonded together. So things or substances either have simple molecular structure like what we just talked about, carbon dioxide, water, chlorine, whatever, or they have giant structures. The word macromolecular means giant three-dimensional structure in which many atoms are strongly bonded together. Now, what examples do we have of giant macromolecular structures? We will talk about the structures of ionic crystals, which we're going to say are called crystal lattice. the metallic structure. So we're going to talk about the structure of metals. Metals are regarded as giant. Diamond and graphite are giant covalent structures, and silicon dioxide also is a giant covalent molecule. So we either have giant ionic or giant metallic or giant covalent like diamond, graphite, and silicon dioxide. So an ionic compound, what is the structure of any ionic compounds? We've talked about ionic and covalent compounds. Most covalent compounds have the simple molecular structures. The ionic compounds have a giant structure, so they are in the form of ionic crystal lattice, in which we have giant three-dimensional structure with regular arrangement of alternating positive and negative ions. So we have, when we have sodium chloride, for example, we don't just have one sodium next to one chloride ion. No, we have a giant three-dimensional structure with many positive, negative in a regular arrangement of alternating positive and negative, and that means each positive ion will have 6 negative ions around it, and each negative ion is surrounded by 6 positive ions. Now, as a result of this, what kind of melting point will it have? It will have high melting point. We're going to say that all giant structures have high melting point. So ionic crystals, for example, they have high melting point because they are held by strong electrostatic attraction forces between the oppositely charged ions. All these positive, negative, when we have oppositely charged particles, they are attracted to each other, and this kind of attraction is called electrostatic attraction forces. So in the ionic crystal lattice, it has a high melting point. Why? Because there is strong electrostatic attraction forces between what? Between positive and negative ions, or between oppositely charged ions. So this is in the ionic crystal lattice. Now, what about metals? Now, metals also have a giant structure, because we said metals have regular rows of positive ions surrounded by a sea of delocalized electrons. So if we're going to describe the structure of any metal, he says describe structure of copper or zinc or sodium, any metal. It has giant three-dimensional structure with rows of closely packed positive ions surrounded by a sea of delocalized electrons. This is because each atom in a metal has 1 or 2 or 3 electrons in its outer shell. It doesn't want it, so these outermost electrons are really a little bit far away from each atom. So now they are not atoms, they're positive ions, and the electrons in the outer shell are referred to as delocalized electrons because they can move around these rows of positive ions. So it is giant three-dimensional structure with what? With rows of closely packed positive ions, because these are solids, of course, so they're all closely packed, surrounded by a sea of delocalized electrons, or electrons that are free to move. Now, why do metals have high melting and boiling points? We're going to say because of the strong electrostatic attraction forces between what? When we were talking about ionic, we said between positive and negative ions. But metals do not have that. Metals have positive ions and negative electrons. Please pay attention. So if we say, okay, if he asks for physical properties of all metals, what are the physical properties of all metals? Please remember, all metals, don't say they are hard, because some metals are soft. Don't say they have high melting points. Some of them are actually, we have a liquid metal at room temperature. Don't say they all have very high density. But what applies to all metals is, first of all, they all conduct electricity. All metals conduct electricity. And you have to remember they conduct electricity both as a solid or when molten. So as a solid or as a liquid, all metals conduct electricity. Now, why do they conduct electricity? Due to the presence of free moving electrons. Remember, we said what was the structure of metals? They are rows of positive ions surrounded by delocalized electrons. So the fact that it has electrons that are free to move, that is why metals conduct electricity. So if we say metals conduct electricity, first of all, both as a solid and as a liquid. Why? Because they have free moving electrons. You should also know that all metals are malleable and ductile. Malleable means they can be spread out into sheets, like aluminum foil, for example. And ductile means they can be pulled into wires. Now, why are metals malleable and ductile? You should know because the layers of positive ions can slide over each other when heated or hammered. So they have layers of positive ions, and these layers of positive ions can slide over each other. So all metals can be shaped. They are malleable and ductile. And of course, all metals are shiny. So in this question, he's saying titanium is a metal. The diagram shows arrangement of particles in titanium. State why metals such as titanium are good conductors of electricity. Do you remember? Why is it that metals are good conductors of electricity? Because they have delocalized electrons that are free to move, or they have free moving delocalized electrons. Explain why metals such as titanium are malleable. Again, why are metals malleable? Layers of positive ions can slide over each other when heated or hammered. Okay, another example of giant substance. This is a giant covalent element. Diamond is made of carbon. Graphite is also made of carbon. So they are all elements, but they are giant and they are covalent because we have many atoms covalently bonded together. So we have diamond, we have graphite, we have also a form of carbon which is called fullerene. Now, what is diamond? So diamond, we said it's a form of carbon. So all the atoms are carbon. But if we're going to explain the structure, of course, we're going to say it has a giant three-dimensional structure in which each carbon atom is covalently bonded to how many? 4 other carbons, and this kind of structure is called a tetrahedral structure. So, to explain the structure of diamond, giant three-dimensional structure in which each carbon atom is covalently bonded to 4 other carbons in a rigid tetrahedral structure. What about graphite? We're going to describe the structure of graphite. We're going to say again, it's a giant three-dimensional structure. In which what? In which each carbon atom is covalently bonded to how many? To 3 other carbon atoms in layers of 6-sided rings with weak attraction forces between the layers. So within each layer, we have strong covalent bonds. Each carbon is covalently bonded to 3 other carbons. But this is made up of layers of 6-sided rings, and there are weak attraction forces between the layers. So let's compare between diamond and graphite. You know that we're going to say that all of them are forms of carbon, so they are actually what we call allotropes. They are different forms of the same element, so they're different forms of carbon. We know what diamond is, and you should know that graphite is, for example, the substance in your pencil. That's a graphite. Okay, so what is the difference between them? If we're going to talk about which one is hard and which one is soft, you should know that diamond is one of the hardest substances that we have. Why is it hard? Because of its structure. Because of the strong covalent bonds between carbon atoms in the rigid 3-dimensional tetrahedral structure. So this makes it hard. What about graphite? We said graphite is soft. Why is it soft? We said because there is weak attraction forces between the layers that allows them to slide past each other, or allows the layers to slide over each other. Okay, what else? Diamond does not conduct electricity. Remember, we said each carbon atom is covalently bonded to 4 other carbon atoms. That means each carbon is in group 4. It has 4 electrons in its outer shell. When it makes 4 bonds with 4 other carbons, it has used up all its electrons. So diamond does not conduct electricity because of absence of free electrons. It doesn't have any free electrons. But graphite, if you remember, we said each carbon is covalently bonded to 3 carbons. Carbon has 4 electrons in its outer shell. It used only 3 of them. So each carbon has 1 free electron floating around. So graphite conducts electricity because it has free moving electrons. What is the use of each of them? You should know that diamond is used in cutting and drilling equipment. Please don't say diamond is used as jewelry. We don't say that. Diamond is used in what? In cutting and drilling equipment. Why? Because it's hard. Why is it hard? Because it has strong covalent bonds between carbon atoms in the rigid 3-dimensional tetrahedral structure. So it is hard because of its structure. Now, because it's hard, we use it for what? We use it for cutting and drilling. What about graphite? Well, graphite, we said it's soft. So because it is soft, I can use it as a lubricant or lubricating agent. Now, we also said that graphite conducts electricity, so we can use it as electrode, and we will be talking about electrodes when we talk about the chapter on electrolysis. So for now, know that graphite is used as an electrode because it conducts electricity. So let's take a look at this question. The lead in a pencil is made of a mixture of graphite and clay. When the percentage of graphite is increased, the pencil moves across the paper more easily. So the fact that we write with a pencil is because the graphite inside moves across the paper. Now, which statement explains why graphite moves easily over the paper? Of course, it's not because it has high melting point or because it's a form of carbon. We said graphite is a lubricant. It's a lubricant, it's soft, its layers can slide over each other because the layers have weak attraction forces between them. Which statement about graphite and diamond is correct? Well, let's take a look. He's saying diamond has high melting point, but graphite does not. Is that correct? Remember that both of them are giant, so both of them have high melting point. He says graphite and diamond both conduct electricity. Which one conducts electricity? Graphite conducts electricity, not diamond. Graphite and diamond both have giant structures. Yes, both of them are giant macromolecular structures. If he says graphite is ionic, that's wrong. Graphite is covalent. Okay, another example of a giant three-dimensional structure is silicon dioxide. So silicon dioxide is a giant molecule with many atoms, but here it is made up of silicon and oxygen atoms. So if we are going to describe the structure of silicon dioxide has a giant three-dimensional tetrahedral structure. So it has a structure similar to that of diamond. But here we have each silicon atom is covalently bonded to 4 oxygen atoms, and each oxygen is bonded to 2 silicon atoms. This is the structure of silicon dioxide. So, if we ask silicon dioxide compared to carbon dioxide, both silicon and carbon are in the same group, but silicon dioxide is a solid. This is actually what we call sand, while carbon dioxide is a gas at room temperature. Why is that? You should realize that when we talked about carbon dioxide, we said it is made up of molecules with weak attraction forces between the molecules, while silicon dioxide, we said, is a giant three-dimensional tetrahedral structure. So the fact that silicon dioxide is solid while carbon dioxide is a gas, this is because carbon dioxide molecules exist independently with weak attraction forces between them. So the molecules are separate and they have only weak attraction forces between the molecules, while silicon dioxide has a giant three-dimensional tetrahedral structure with many strong covalent bonds. So this will need a lot of energy to be broken, so it will have a high melting point. Explain in terms of structure and bonding why silicon dioxide has a high melting point. Again, why does silicon dioxide have a high melting point? Because of its structure. So because it has a giant three-dimensional structure with many strong covalent bonds that need a lot of energy to be broken. If he's asking diamond and silicon dioxide both have giant structures, which of these statements are correct? Well, let's look at the statements. He's comparing diamond to silicon dioxide. Both substances are compounds. Is that right? We said diamond is made of what? Diamond is made of carbon. So actually diamond is an element. Silicon dioxide is made of silicon and oxygen, so that's a compound. There are many strong covalent bonds in diamond. Yes, that is correct. There are many strong covalent bonds in diamond. Silicon dioxide is bonded ionically. Is silicon dioxide an ionic compound? No. We said it's a giant covalent, just like diamond. Both substances have very high melting points. Yes, because both of them are giant three-dimensional structures. So which one was correct? Statements 2 and 4. 3 statements about diamond, graphite, and silicon dioxide are listed, and which statements are correct? So let's take a look at the statements. Diamond and graphite both have giant covalent structures. Yes, that is correct. Diamond and graphite both have giant covalent structures. What about the second one? In silicon dioxide, silicon and oxygen atoms are joined together by covalent bonds throughout the whole structure. Yes, that is correct. We said it's a three-dimensional tetrahedral structure in which there is covalent bonds between all the atoms. So that is correct. Diamond and silicon dioxide have similar structures. Yes, we said diamond and silicon dioxide both have giant three-dimensional tetrahedral structure. So actually all these statements are correct. Okay, another form of carbon is fluorines, and fluorines are made up of 60 carbon atoms joined together in a structure of pentagons and hexagons that is arranged in a sphere. So actually this is just a molecule made of 60 carbon atoms. This is regarded as a simple molecular structure. So this is not a giant structure, and as such they have lower melting point than graphite. This is because they have simple molecular structure with weak attraction forces between molecules that need a small amount of energy to be broken. So just keep in mind that fluorine is a form of carbon, just like diamond and graphite, but the difference is diamond and graphite are giant. Fluorine is a simple molecular structure with weak attraction forces between molecules, so it would have a lower melting point. So there is a question that says doctors use C60 fluorine to deliver medicines to certain parts of the body so that the medicine does not damage other parts of the body. Suggests why C60 fluorine is suitable for this purpose. Remember, we said fluorine is a small molecule and it's in the form of a sphere, so you can put a medicine inside the fluorine and you can inject it into certain parts of the body, and that is okay because fluorines are not reactive. They will not react with the medicine and it is not toxic, so that is useful for this kind of medicinal purposes. What about this other question? He's saying describe in terms of electrostatic attractions the bonding between the atoms in copper and the bonding between the atoms in graphite. What did we say about copper? Copper is a metal. What kind of attraction forces between the atoms do we have? We said in copper we have layers of positive ions because the outermost electrons are floating around, so the atoms are in the form of positive ions. So the attraction forces that we have in copper or in any metal are strong electrostatic attraction forces between the positive ions or the positive nucleus of the atoms and the delocalized negative electrons that are floating around. So that is the interaction that is holding them together. What about graphite? Now you should remember that graphite have covalent bonds. What kind of electrostatic attractions do we have in a covalent bond? So you're really actually explaining covalent bonds. Remember, you're not explaining the attractions between the layers. The covalent bonds, if you remember when we were defining covalent bonds, we were saying the covalent bonds are strong electrostatic attraction forces between the positive nuclei of the atoms and the bonding pairs of electrons in the covalent bond. Explain how copper conducts electricity. Remember, copper is a metal. Why do metals conduct electricity? Because they have delocalized electrons that are free to move. The sea of delocalized electrons are free to move. Explain why graphite has a high melting point. Well, graphite has this kind of giant three-dimensional structure with strong covalent bonds. So the strong covalent bonds between the carbon atoms in the giant three-dimensional structure, so we don't just have a few bonds, we have many strong covalent bonds. So these need a lot of energy to be broken. Another question says titanium chloride and titanium oxide are both covalent compounds, but titanium chloride is a liquid while titanium oxide is a solid with high melting point. So he's saying titanium chloride has low melting point, titanium oxide has high Explain these properties in terms of the structures. So if I tell you that titanium chloride has low melting point, we said anything with low melting point has simple molecular structure with weak attraction forces between the molecules that need a small amount of energy to be broken. While if he tells me that titanium oxide has high melting point, then that means it has a giant covalent structure with strong covalent bonds that need a lot of energy to be broken. So please be able to apply what we said to any other examples. Then this question says the table shows boiling points of some compounds containing silicon. All of these compounds are covalent. They have covalent bonds. And again, he's saying silicon tetrafluoride and silicon tetrachloride have simple molecular structures, while the silicon dioxide has a giant covalent structure. Explain why the boiling point of silicon tetrachloride is greater than the boiling point of silicon tetrafluoride. So if I tell you that both of them are simple, so both of them have relatively low boiling point. Now, why would one have lower than the other? If both of them are simple molecular structures, if that means that the one that has higher boiling point, so silicon tetrachloride has higher boiling point, that must mean that the intermolecular forces or the attraction forces between molecules in SiCl4 is stronger. So both of them are covalent, both of them are simple. So both of them have weak intermolecular forces, but if one has higher boiling point than the other, then the one that has higher boiling point has stronger intermolecular forces or stronger attraction forces between molecules that need more energy to be broken. What if he's saying, explain why the boiling point of silicon dioxide is very much greater? Well, if it has very high melting point, that is because it has strong covalent bonds in the giant structure that need much more energy to be broken, while the silicon tetrachloride has weak intermolecular forces. And that's the end of this part of the chapter. Thank you for listening.